Okay, I have to apologize. I got it wrong on the announcement. I announced the wrong infinite series. The infinite series that I am interested in is the one that goes like 1 minus a third plus a fifth minus 7. And if I don't err, that's equal to pi over 4. And I don't know, I was thinking how to sort of begin this lecture, and there's a sort of this chap named Abhyankar, an Indian mathematician at Purdue, and he has this concept of dividing mathematics into sort of different levels, and his favorite level is what he calls high school mathematics. And high school mathematics essentially is anything that he likes. But I mean, one could conceive of high school mathematics, and then there's sort of college mathematics, and then there's sort of graduate school mathematics, and then there's sort of, I don't know, I mean, sort of, you can sort of nursing home mathematics, what you sort of you do in your dotage. But if you look at an equation like this from the point of view of high school, right? I mean, first of all, you'd be very excited, right? If you had any mathematical taste at all, obviously it's a thrilling equality. And beyond that, well, you'd probably know that pi had something to do with a circle. But other than that, you really probably wouldn't know what to make of this thing. So somehow there'd be some notion of a circle, and then you'd be sort of stuck. But now in college, of course, college mathematics. Right, well, in college, you'd learn about, I don't know, the Taylor series expansion for the arc tangent, or in fact, I don't know. I forgot to look it up. But so anyway, so if you'd learn about Taylor series, and you'd be able to prove this formula. Okay. And then in graduate school, right? Well, graduate school, I mean, obviously you'd have nothing but contempt for such a formula. I mean, there's sort of no sex at all, and I mean, you know, you want to look at perverse sheaves or something. You don't want to look at this thing. And so it would sort of only be, you know, when you get to like sort of nursing home. Mathematics, where you're sort of sitting there reminiscing about all your sort of mathematical experiences, and you come back to a formula like this and say, gee, that's really a nice formula, you know, sort of think about it a little more. So from that point of view, I'm not yet in a nursing home, but sort of going that direction. I mean, sort of the derivative points that way. You look at the formula like that, and you say, gee, when I was in high school, I really liked that formula, and I realized that the thing on the right-hand side had something to do with the, you know, the radius, or the, what is it called, the circumference of a circle or something like that. Maybe one could prove that formula by somehow, does the left-hand side have something to do with a circle, right? And so, you know, you think about it a little bit, but by the time you get to nursing home, you've seen a whole lot of mathematics, and you realize that there's circles and there's circles, right? And if we look at the equation, an algebraic geometer, well, he sees that equation sort of in lots of different, there are lots of different sort of avatars of that equation, and I could view that equation over a finite field, for example. I could look at that equation over a finite field, or I could look at over a p-adic field. Maybe I should. Does everyone know what QP is? Well, I mean, it's the quotient field of ZP, and this is the p-adic numbers. Okay, so this is sort of power series in powers of p, and this is the quotient field of that. Okay, so it's a nice topological field. It has a nice topology. Points are close together if their difference is divisible by a large power of p. And we could look at the solutions of this equation with coefficients in QP. And so what happens? Well, we could look at it, right? Let's call this locus of solutions of this equation, call it, say, T. And, it sort of breaks up into two possible cases. Let's leave out the case p equals 2, because I don't have much time, and that's obviously a confusing case. But if p is not equal to 2, then there are two cases depending upon whether -1 is a square or not in this field. Okay, so there are two. Okay, and it turns out that -1 will be a square if p is congruent to 1 mod 4, and it won't be if p is congruent to 3 mod 4. Okay. So now we want to pi, or 2 pi, or whatever, is after all the sort of the volume of a circle, right? If we look at the volume of the real points of this T here, right? That's 2 pi in some sense. Right? So we might be led to look at the volume of T of QP. Well, that's not so good, in fact, because it's too big. So it's better to look at the volume of T of ZP. So the solutions of this means the solutions of this equation with values in the ZP. Okay? Well, how do we think about that? Well, this is sort of a bizarre topology on this guy. And you think of if you look at Z mod PZ, that's the finite field with P elements, the Galois field with P elements. So if you look at the solutions T of ZP, you can think of that as being a sort of a collection of, sort of a vaguely circular collection of disjoint balls. Depending upon, I mean, if we have a point in here, let's say we have a point, what should we call it, say x1 and x2 in there, then we can send that point to, so to speak, x1 bar, x2 bar. So this is a point in ZP taken twice, and this is a point in the residue FP taken twice. And we can use this game to sort of put an equivalence relation on points. The different balls here are those which specialize to the same point here. Okay, so these are the different values in FP squared. Now, it's sort of natural to think of the volume of ZP to be 1, right? And it's also the case, although I guess I won't take the time to show it, that sort of there's a nice, you can do analysis, you can do p-adic analysis, you maybe heard the phrase, and if you do that, then locally, analytically, this is like ZP. And these little balls here are, each one can be thought of as like the P times ZP. They're all congruent to each other mod P, so each little ball is like see, this contains all the numbers that are divisible by P, and the index is, of course, P, so therefore the volume of this thing is 1 over P, right, to make the game work. Of course, I'm talking about what's called a Haar measure. I want the measure to be translation invariant under addition. And so there's sort of P different ones of these guys that fit and make up this guy. So each of those has volume 1 over P. And so, therefore, we can say that the volume of this T ZP is equal to, well, the number of these balls is the number of solutions in FP, and each ball has volume 1 over P. Okay? So, well, how many are there? Well, an elementary exercise to convince yourself that if minus 1 is a square, that is, if P is congruent to 1 mod 4, so the number of elements in TP, T of Fp, is equal to P minus 1 if P is congruent to 1 mod 4, and it's equal to P plus 1 if P is congruent to 3 mod 4. Okay? So, therefore, the volume of T of Zp is equal to, what is it? It's equal to 1 minus 1 over P, if P is congruent to 1 mod 4, and it's 1 plus 1 over P, if P is congruent to 3 mod 4. And therefore, the left-hand side of this mysterious equation, if you do a little manipulation, you find that this is equal to the product for P not equal to 2, we leave out P equals 2, of the volume of the T Zp, and these numbers, inverse. Inverse. Okay, I think you can manage that calculation, right? I mean, you just have to think about that for a little while. Or said another way, well, it's not quite equivalent, but it's clear that that implies that if we take the volume of T of R and we multiply by the product of the volumes of the T of Zp, well, what do we get? I mean, well, I don't know. We get something like 1/8, or maybe it's 2, or some. We've got the volume is 2 pi, and we're multiplying by the left-hand side here, so that's equal to 2, right? I think it's 2. In any case, it's some non-zero rational number. Okay. Now, you see, we begin to see here that maybe there's something fairly general going on, right? And in fact, this whole line of inquiry was formalized by Tamagawa. And so to say things slightly more formally, this T is a torus. It's an algebraic group, defined by equation, and it's also a group. I mean, the circle is a group, has a group structure. And more generally, if G is, let's say, a reductive algebraic group, well, just don't worry reductive, just think of G as being GLN or any one of, something that you can sort of make sense of, values, its points with values in some field. T is one such thing. Then one knows that if suppose that the dimension of G, let's say, is D, then one knows that there's this notion of a translation invariant differential form for G. So one can choose, there exists a non-zero left invariant differential D form on G. And one of the nice things about being an algebraic geometer is that you don't have to worry about all this game is played algebraically. So this D form, let's call it something, depth invariant differential G form, say omega on G. And omega, let's suppose that our group G is defined over Q. That means the equations defining our group have coefficients in Q, which they do in this case. Then this omega we can take to be defined over Q also. Now, if we look at any one of our field Q is contained in QP, and the number theorists like to write R equals Q infinity, sort of completion at the infinite prime, and so therefore we can think of omega QP for all P less equal to infinity. Now the point is that it's kind of well understood that how to, given a, if we look for example at omega R, this is a translation invariant D form, and it defines a Haar measure on the real points of G. It defines a Haar measure on the real points of G. For example, if our group G, let's say, was the multiplicative group, somebody pointed out yesterday, this is GL1, then it has a coordinate t, and we could take omega to be dt over t. Okay. So these guys, now slightly less well known, but basic to Tamagawa's work. We're not talking here sort of the latest hot poop. This Tamagawa did his work in, I guess, the early 50s. The basic observation of Tamagawa was that this same game was playable p-adically. That if you looked at omega QP, this defined a Haar measure on the p-adic points of G. Essentially, you could write this, you see locally, you could write this in the form F dz1 wedge dz little d, where d is the dimension, and you could think of z1 up to zd as being local coordinates, which, so z1 up to zd, you can think of that as sort of a local coordinate patch identifying a little piece. So if we take GQP, and then there would be some sort of little p-adically open neighborhood of the point where you were studying things, and this would be identified with ZP to the D. And if you think of this as having measure 1, and sort of that normalizes a Haar measure here, and that then gives you a measure on this little open set U, and then you change it by looking at the p-adic absolute value of this function f times, so to speak, the measure that I've just described here, call it, say, dz1 dot dzd, and modify it by whatever the p-adic absolute value of this function at any given point is. This is invariant under the choice. This defines a local measure on U, which is invariant under the choice of these, the usual determinant transformation. So it defines actually a global Haar measure on these points. And this was Tamagawa's observation. Well, so what? Well, you see now a beautiful, an extraordinary thing in fact happens. Namely, these measures, see I wrote over here, I said that the measure of T of R was 2 pi. And everybody said, sure, we all know that the circumference of a circle is 2 pi, but that's only a circle of radius 1, right? And the point is that there's no canonical choice of this omega over q. There's no canonical way to pick it out. And if I think of omega over q as defining omega over r, and as defining omega over qp, these guys depend on the choice. In fact, if I change omega to, let's say, a times omega, then if I look at a times omega at qp, this is equal to the p-adic absolute value of a, that is the number of, well, let me put it this way, where this means the absolute value that associates to p the value 1 over p, and to p to the n the value 1 over p to the n, and so forth. So if things are p-adically close together, they have a small absolute value. So now the point is that with this in mind, and of course p infinity is just the usual absolute value of p, namely it's p, we find that the product for all p less equal to infinity of the p-adic absolute value of a is 1, because a is some rational scalar. So what happens in real life is there's a one-dimensional vector space of these omegas. If we choose a different one, or the choice changes the various p-adic measures as indicated here, but the product doesn't change. So that means if I denote by G of the Adels what is essentially a sort of restricted product of the G of qp for p less equal to infinity, a restricted product in order to make the thing, a restricted product means I take elements in the product, all but a finite number of entries of which are sort of small. Let me be a little cavalier about that. But in any case, I make the appropriate movements to guarantee that this thing is a locally compact space. See, the problem is that G of qp in general is not compact. So if I take an infinite product with an infinite number of non-compact spaces, I have a recipe for a mess. So I just modify things. Anyway, this is then a well-defined guy. It's a group, and he has a canonical measure. He has a canonical measure. This choice of omega washes out. Now, of course, you say, but when we did this calculation for t, we didn't take the volume of t of qp. We couldn't. It was too big. It was infinite. We took the volume of t of zp. Well, similarly here, if we compute the volume of this whole space for this measure, it's going to be infinite. So we got to make it smaller, but there's a natural way to make it smaller. Namely, this contains as a discrete subgroup G of Q, just the rational points. The rational points. You see, we sort of didn't need the rational points. Well, okay. And, sorry? No, not in general. Might be, but in any case, cofinite measure. Okay? The point is that the measure, so let's call it straight lines omega, of G of AQ slash GQ is less than infinity, and the Tamagawa number conjecture, which has really been proved now for all but a few extremely recalcitrant twisted forms of E8 or some, essentially this is always true. So I'll put an exclamation point and a question mark. indicate essentially this is always known, is a non-zero rational number. A non-zero rational number. So therefore we can read back this kind of calculation that we did here and find essentially that something like, so roughly we find the volume of G of R slash G of Z times the product of the volumes here, but we sort of did a calculation, and the same kind of calculation works in general. Namely, this volume is the number of points of G with values in the finite field divided by P to the D, where D is the dimension of G. This expression here, roughly speaking, belongs to, is a rational number. Okay. Well, that's all well and good, and that's been sort of well understood now for, well, there's been improved results and Langlands and Kottwitz and all kinds of heavy-duty mathematics that went into proving these kind of theorems. But I'm sort of interested in how this might be generalized to algebraic geometry. And it turns out there is a generalization, and that's what I want to talk about now. So let's try and get a little more algebra geometric, and rather than T, this torus, or G, this more general kind of reductive group, let's talk about A, which is an abelian variety. An abelian variety. Okay? And we might try to calculate the volume of A of an abelian variety, let's say, over Q, defined over Q. So I should tell you what it is in abelian variety. Well, the complex points of A as an analytic space are of the form C to the D. D is still the dimension of A. Modulo some lattice, call it lambda, where lambda is isomorphic to Z to the 2G. So sort of as a complex analytic space, it's a quotient 2D. It's a quotient. I mean, sort of think of a fundamental domain, CD, analytically, like that. Or since we're going to be wanting to talk about little sort of number theory kind of things, and this is really not an adequate description from that point of view, you might consider the case where where D is 1. So in case D equals 1, in that case A is what's called an elliptic curve. It's defined by a cubic equation in two variables. So it's the projective completion, if you like, of an equation like y squared equals x cubed plus ax plus b. Things where a and b are in Q, and then the point is, you see, this is a thing of degree 3. It's a thing of degree 3. So if you take 2 points here, let's say alpha and beta, then you can draw the line through them, and it will meet the curve at a third point. And you say by fiat that this third point you're going to call, quote, minus alpha minus beta, quote. And you discover that that rule defines for you an abelian group law on the points of this thing. So this rule makes A equals an abelian algebraic and more generally in higher dimensions, although I don't know how to draw the picture. So we could try to look at the volume of this kind of a quotient. Okay, well, there's a nasty problem here, which turns out not to be a problem, but I want to dodge it. And that is the problem I'll just mention is that this space here is compact. This is compact because A is complete. You see, it has no holes, so this is compact. So if it has an infinite number of rational points, which it frequently does, there's no way this quotient could be a nice Hausdorff space. Okay, well, don't worry. I don't have time to get into how that. So this is in general not Hausdorff. So what you have to do is take some extension of A. There's some canonically defined extension of A, and achieve in that way a Hausdorff space. This corresponds to the fact for the cognoscenti that the L function of A and S has a 0 at S equals 1. I should have mentioned in connection with this kind of calculation here that formally this product over the finite primes looks like the value of some L function at the point S equals, well, at some point. L functions, well, you don't need to know too much about them to live a good productive life, so we won't get into that. So, okay, we could still try by the same kind of techniques by taking an omega, which is in the highest exterior power, so the sort of the determinant of the space of the invariant tangent vectors dual, so I get cotangent vectors, and as before, so defined over Q. And this defines a volume, and we can talk about this volume. And roughly speaking, the resulting conjecture, so again I stress roughly, the conjecture is that the volume for this measure of A of Q over A, Q should be in rational number, is the so-called Birch and Swinnerton-Dwyer conjecture, roughly. I'm dodging a sort of technical point. Not a technical point, I mean a basic point. Okay, but so Birch and Swinnerton-Dwyer, they did their work in the 60s. You know, we got a ways to go still. So let's try to make sense of this thing from the point of view of motives. Well, I haven't told you what motives is. I don't want to assume that whoever is here was here yesterday. So let's just start out. We want to talk about, we have our abelian variety. We'd like to talk about its points with values in QP. Okay. In fact, I can say as a topological group, it turns out this is isomorphic to QP to the D plus to ZP. Sorry, ZP to the D direct sum some finite torsion. Finite torsion group. So it's a very reasonable topological group if you swing with p-adic things. And so one way to think about this group is the following. if we can use sort of Galois cohomology, let's see, how do I want to say this? Yeah, let's use Galois cohomology. If we look at the points of A with the solutions of A with values in the algebraic closure of QP, then we're going to get a picture that really is rather more like, let's see, did I erase it here? Yeah, remember I wrote A of C was C to the D modulo lambda, right? So vaguely speaking, what's going to happen if I look at the solutions with values in the algebraic closure, and I look at, let's say, a map which is, say, multiplication by some integer n, then what's going to happen is very much the same thing as if I considered multiplication by n on a group of this shape here. So what would happen if I considered multiplication by n on a group of this shape here is I would get a little exact sequence. I would get, so to speak, 1 over n times lambda divided by lambda goes to this CD mod lambda goes CD mod lambda goes to 0. I get a little exact sequence like that where this is multiplication by n. And similarly, in this more algebraic situation, I get something like this. This is not what I want. 0. This is not 0. What comes here is the kernel of multiplication by n on these points. Okay? And now the Galois group operates on these points. Operates on everything. And so if I take the invariants, the points that are invariant under those Galois group, I'm going to get back the points that are defined over QP. But on the other hand, multiplication by n is not necessarily going to be surjective on those points, and the error term is going to be read by the higher cohomology. There's a long exact sequence of cohomology associated to this, just like in topology. So we can sort of imitate the way one always studies cohomology, and we can get A of QP. Now no bar, I've taken invariance, multiplication by n, A of QP, and here comes H1 of this, let me call it GP, GP, with coefficients in the kernel of multiplication by n GP bar. And then here comes H1 GP with coefficients in A. So things are getting a little more sophisticated here. But the point is we now can sort of take a limit over n. And this group here is clearly an adically complete group. That means if I take this group mod n for various n and then pass to the inverse limit over sort of more and more divisible n's, I get the group itself back again. So if I play that game here, what I find is an injection into H1 GP with values in a certain inverse limit of A of QP. Okay. Now I can rewrite this thing as being H1 of GP. So now gradually things are getting a little more sophisticated here, but I hope at least the thread is clear, even if you haven't thought carefully about these various ideas. with coefficients in, and now I want to use, I have to use, I don't want to use, and I'm stuck with using, a little bit more about the theory of abelian varieties. Namely, every abelian variety comes equipped with a dual abelian variety. A hat, let's say, which if A of C, for example, was C to the D mod lambda, then A hat of C would be C to the D modulo a certain dual lattice where there's a whole song and dance here about polarizations, the bottom line of which there's a certain canonical skew symmetric form, and it makes sense to talk about the dual lattice. And so there's a certain duality, and the point is that A hat of C is sort of the Picard group of line bundles, sort of topologically trivial line bundles on A. And vice versa. This is A hat hat is A again. And what happens is that this kind of limit, this should be the limit over n of the n torsion points. This kind of limit here has an interpretation as the étale cohomology of A hat with coefficients in QP, with coefficients in, Z hat of 1. Okay, now things are getting a bit more technical, but for those of you who came to the lecture yesterday, I talked about this notion of motives, and the basic idea of the notion of motives is if I gave myself a variety X, let's say a smooth projective variety, let's say over Q, and I give myself a cohomology group, let's say Hn X, and I give myself a twist. Basically, I give myself X and I give myself two integers N and R. Then there is a sort of a universal such guy, which you can think of as being associated to the nth cohomology group, for example, the nth Betty cohomology, the usual singular cohomology of X. But it's universal. It has its realizations, all the various kind of cohomology theories. And this R here can be thought of as follows. If I look at the what's called the étale cohomology, well, technically, you write it like this. You take some L that has nothing to do with anything, and you could define a cohomology group. The point is this is a cohomology group which in algebra plays the same role as the nth Betty cohomology, but the difference is that the Galois group of Q acts on it, and when they have that kind of action, you can define an L function. I'll just call this H, and S, by looking at the determinants of the various Frobenius elements in here acting on H. So there's a certain L function here. I'll give an example at the end of the lecture, but I don't want to get too much into it. But the point is that the R here is just a placekeeper for the S. So if I twist by R, then the resulting S is translated by R. So the R that appears here should be just thought of as a twist or a placekeeper. But when you go through this business, what you find is that the points, the thing that I want to measure to get my Tamagawa number, sit inside this kind of thing. Well, in fact, what happens is that this thing gets identified with the extensions in the category, in a suitable category of motives of Z by the motive H1 of a hat Z hat of 1, and the motives are over QP. Okay, well now things have gotten to be totally mysterious, but the extraordinary fact is that the whole discussion that I went through generalizes. Namely, there's a measure on this X group so sort of amazing fact is that we can make sense here. I guess for this discussion here, I'm thinking of as p less than infinity, but we can also make sense. If time permits, I'll explain how, of the corresponding X1 of motives over R of Z by H. And now let me shift. Obviously, at this point, any reference to abelian varieties is completely irrelevant, so I'll just take my general Hn X Z R, and these groups, let's call this, let's say, E R, and we have the E QP, and these groups have measures, and one can conjecture and prove in a limited number of very special cases that if one looks at the volume of the product, or restricted product of P less equal to infinity of the E QP modulo E of Q, and therein hangs the tail. I have to, well, I won't, but I should explain what this means. This should be a non-zero number, and to be more precise, to avoid technical things, this should be the case if the numbers are right. So n, I want that n minus 2r should be less equal to minus 3. And in other cases, suitable modifications of this game should be playable. So you see, we started with 1 minus a third plus a fifth and so on equals pi over 4, and we ended up with some sort of extraordinary, bizarre looking thing which can be sort of a super generalization of this. So maybe just to finish up, I kind of despair of explaining in any more detail what happens at the finite primes, but let's at least look at the infinite prime in complete generality. Good, I've got 5 minutes. It should just about work. So, in other words, I'd like to now explain what, in general, appears on the right-hand side of the resulting equation. Just vaguely, the left-hand side is going to be some value of some L function, closely related to it. So let me just explain what is E R. Well, we started now with this sort of more general gadget. So let's suppose that, I can now look at, and I assume that everybody is familiar with, if I look at the X is a variety over Q, so I can look at its complex points, and I can look at its complex cohomology, and I can factor out by, what do I want to factor out by? FR. So this is the sort of the rth level of the Hodge filtration. And it is generated, if you like to think in terms of differential forms, you know, you can give forms type PQ forms, and these are forms, so forms with at least R holomorphic parts. Okay, so that's a certain subvector space in this complex vector space. And I also factor out by Hn xc with coefficients in a certain subgroup of this coefficient group, and the subgroup is just z times 2 pi I to the power n, n power r. Just think of this thing as contained in there. So I take that quotient there, and my omega is to be a non-zero element in the, now I have to talk algebraic geometry talk, the de Rham cohomology is sort of just a way of playing this game, but over Q, and I take the determinant of the nth, the de Rham cohomology of x over Q, dual, and omega c, the complexification of omega, then defines for me a measure on this group here. Now actually I've written down this group here is E of C, so I actually, there's a conjugation, an action of conjugation, so I'll put a little plus here to take the part invariant under conjugation. And the E of R is then this, and its volume is then computed with respect to this kind of a measure. You see, this is a nice, it turns out with the conditions I've imposed on N and R, this is a nice abelian Lie group. It's sort of a vector space modulo. It turns out this is a discrete lattice in there. And so it's a nice abelian Lie group. It has a nice measure on it. Not necessarily a co-compact lattice, but it has a nice measure on it. And the volume, then the possible failure of co-compactness here is made up for by the existence of these rational points, which I haven't talked about. And it's the volume then, so to speak, the right-hand side of the original equation is then the volume of this E of R modulo, so to speak, E of Z. Now I should mention, just to finish, that this is of course not all due to me. The ideas in here come from work of Deline, Valenson, and my joint work with Kato, Kazuya K. Kato. Okay, so long.
What kind of numbers do you generate out of this?
Oh, it's a good question. I mean, values of alpha. Well, this, you would say that an L function would be, see, a simple case, for example, suppose I took an elliptic curve. Okay, that A of R, you see, if you sort of know what an elliptic curve looks like, right? You'd be looking at the real solutions of the cubic equation. So that would either be like that, or else it would be just like that. And we'd be computing the integral, we'd be computing the classical integral of suppose your cubic equation is y squared plus x cubed x b, or more generally y squared some function of x, then you'd be computing the integral over the sphere locus of, it's the usual dx over the square root. Yeah. Y. It's the classical elliptic integral. And the conjecture says that the classical elliptic integral is equal to a product which in fact turns out to be, or the reciprocal rather, the product which turns out to be the value. Essentially it says that this elliptic integral multiplied by the product of number of solutions on an elliptic curve b divided by b should be that. That's versions of the environment used to actually compute this product. Used it. I mean, they couldn't. It doesn't converge, but they did it anyway. They had a real big computer, right? So they went out really far, and they sort of claimed that the resulting thing. Well, Swinners and Dyer claimed the resulting numbers were evidence for the conjecture. Birch never made such a claim. Well, it turns out that you can't do that. You have to analytically continue the element side. That's sort of thing. Absolutely. So, a physicist at least would have something to converge in the end. You might cheat and lie and steal to get there, but he has something that converges in the end. This doesn't converge.
So you have to regularize.
Well, it's the limit. I mean, it's a Euler product for an analytic function. Yeah, Hato has proved it for the Riemann zeta. It's not true. The point is, so x, in other words, take x to be spec cube, which is just a point, but different value